So continuing on the theme of pandas, but kind of going to a totally different sort of project. Great, can you hear me? Yeah, okay. Yeah, so as Devin said, my name's Caroline. I've been really lucky to work on this project on program synthesis for the Pandas library with Rohan and Lemieux, among others. They're sitting in the back and they'll be coming up during the tutorial portion. But I wanted to just start by giving you kind of an overview of what this project is all about. So the story I tell here about this project is that, in recent years we've witnessed this huge explosion of APIs that developers need to be familiar with in order to write efficient, performant code in the modern software systems. And learning to use these APIs effectively is quite a difficult task, right? Now, a lot of people cope with this by turning to things like Stack Overflow, and you kind of learn how to do things by writing down an input-output example and hoping that someone on Stack Overflow will answer it for you, right? But in reality, this doesn't always work out. Sometimes you'll get redirected to basically the documentation and you're just as lost as you were when you started. People might give you inefficient solutions, or they might give you solutions inefficiently, like 4 days after you encountered this problem during development. So the big goal of this project, right, is can we automate some of this process, kind of build a system where I will give you an input-output example, and you will tell me in this API, this is the program you should use to get from that input to that output. And in this case, we're looking at data frame transformations. So let me give you kind of a roadmap of where I'm going here. First of all, I'm going to talk about why program synthesis is kind of the technique we're going to use here to solve this problem, and also give you an idea of why we came up with a totally new technique here. Then I'm going to give you a really high-level overview of the technique. If I have time, I'll show you a bit of a demo of how it works. And then Rohan will do a deep dive in the tutorial of actually show you how you can build a synthesis engine for a subset of pandas. All right, so let me get started. So remember, we have this question. We kind of want to build this auto Stack Overflow engine that will give us the programs that fit our input-output examples. Kind of zooming out, this is the problem we have. We're a developer. We have this input data frame. We know we want to change its format slightly, but we don't know the pandas commands that will do that. So we ask our system, and it gives us the pandas programs that takes the input and turns it into the output. Now, if you see what we have here, we have a specification and a program. And here the specification is your program should take this input to this output. And at a high level, that problem of given a specification, come up with a program that fits that specification is a program synthesis problem. So there's been some work in program synthesis. Maybe the thing that's most popular is flash fill in Microsoft, where you can basically synthesize how to do different string transformations. So if you look at the domains that people are tackling, you have these domains of these small languages of, say, string transformations. And there has been some work on, say, R APIs, but again, people tend to focus on a subset of 10 API functions. And the thing is, to build all these systems right now, you need like a PhD student in PL to come up with formal semantics and heuristics to build each of these synthesis engines. Or in the other case, you need another PhD student in PL to come up with formal semantics for formal specifications for the APIs. And this process of needing a PL expert to formalize all of these real-world APIs really doesn't scale to real-world APIs when the semantics of those are rapidly changing and the APIs are huge, right? Like, if you look at the Pandas library, there's like hundreds of functions, and each of these functions has, especially because it's Python, has really complicated arguments, which it would take a lot of PL PhD students to find a way to formalize this properly. So this is why So this is the problem with the current synthesis techniques. So let me now give like a really high-level overview of how our AutoPandas system kind of works. And the idea is as follows, right? Again, you have an input-output example. You want our AutoPandas system to give us the program in pandas that transforms the input into the output. How do we do this? It's basically like a guess and check approach. You have this program candidate generator. And what that thing does is it's a program that generates pandas programs. For example, when you call it, it might generate this program, right? This program does a melt and then a pivot. And now AutoPandas is going to check if that program turned my input into my output. In this case, it does not. So it goes back to that program candidate generator and asks it, hey, can you generate another pandas program? And it generates another random pandas program. And this one also doesn't match the input-output example. And what you would do here is then repeat that many, many times. Keep calling that generator and generating new programs and checking whether they match the input-output example. And eventually, you know, if this is exhaustive and covers all the pandas library, this will eventually get you a program that, when applied to your input, gives you your output. And now you're done, and you output that. Okay, that's the big picture. I'll get to a performance issue very quickly. But let me first start by talking about what this program candidate generator is. Because this is one of the key differences between our techniques and other ones. We're not writing total formal semantics for pandas. I don't want to do that, and I don't think Rohan wants to either. Instead, what we do is we encode the domain knowledge about the API in this program candidate generator, which right now is written just once by the API expert. And what does that do practically? It does something like this, right? So you want to generate a pandas program, given some inputs and some output. So maybe the first thing you should do is select a sequence of pandas functions that you need to apply to get from the input to the output. So here, this purple sequence operator, you can think of it, it's returning a random sequence of that list it has there, and that list has all the pandas functions. Okay, now you've selected a sequence of functions, and you need to select which, if you have multiple inputs, right, you need to select which one you should apply that sequence of functions to. So again, this select gives you one of your inputs, kind of at random. And then for each different function, you need to populate arguments. So for example, if you had the pivot function, you know that this first column here needs to come from the columns of the data frame. And the nice thing this first argument, sorry. And the nice thing here is that you can directly use the pandas API to build this generator, saying, right, how do I access the columns? It's with this dot columns, right? I didn't have to write a new kind of language to talk about this. And you might also know that the second column can't be equal to the first one, right? So you could say, okay, select a column, but did not accept the first one. Okay, then you would add the arguments to the function, and you would have this kind of in concept for all the other functions in your library. And at the end, you would return this function sequence with arguments, and it would be kind of all populated sort of randomly. Right, and what you can see here is that we're capturing that key domain knowledge about how the inputs relate, how the arguments relate to the inputs in native Python code. Okay, now you may be thinking, how many random pandas programs does it take before I find the one that actually matches my input-output example, right? And great question, and that is like what if it takes 100,000, right? We're never gonna get there. So kind of the question we have to ask here is, well, in what order do we generate those programs? That's the key problem with this approach, right? We don't know how to generate the programs in the order we want. So what we can ask is, what is it about this generator that governs the order in which we return those pandas programs? Really what governs the order in which we return those programs are these kind of non-deterministic operators, right? The one that shows the sequence of functions, the one that shows randomly which column to use as the arguments. You can think that if it's on the 100th guess that we choose the correct sequence of functions, it's gonna take us forever to get the right program. But if we could get it to, look at our input-output example and kind of condition the randomness based on that input-output example, then maybe it could output the correct sequence in the first try. So that's kind of our second key insight, is to replace these non-deterministic operators, instead of just searching randomly or exhaustively, by some sort of smart model, which I don't have the time to get into how we do that. Rohan will touch on it in the tutorial. But the key idea is that basically we can learn for each of these non-deterministic call, like the probability distribution given the input-output example that will give us, with high probability, the total program we want that takes the input to the output. And we use deep learning here. So let's see if I can do this very quickly. We deployed AutoPandas on the internet, and this is one of the interfaces in which you can use it. You can add your inputs examples and have your output data frame. Let me just load an example that exists. You write the data frames in native Python code, and you can preview them. It takes some time for the things to warm up, and you can actually, directly edit the data frames here and have that be, oh, that's not what I wanted to do. Okay. You can actually directly edit the data frames in the preview and have that actually be reflected in the code. And same thing with the output example, the output from your example. Anyway, and the point is that now you have your input-output example, and we submit the task to our AutoPandas engine, and hopefully, yes, there we go. It will give us the pandas program that performs that transformation much faster than it would to ask a human on Stack Overflow. All right. In closing, so we released that AutoPandas web service back in May. The framework that Rohan's going to talk to you about, we released this summer. And Lian Min's been working on extending this to the NumPy library as well, since we think that's a really important target. And now Rohan's going to give you a tutorial on how we actually build this. Thanks. If you have any questions before he starts. Right, so the question was about, could we use genetic programming to kind of generate that program? Or some other kind of, so I think the neat thing about this approach is that, so it's not totally dumb because all those like conditions on the arguments are encoded in that generator. And then the question is, how do we like still search that space well? We've mostly explored, in this project, we've mostly explored using like neural models to back the randomness. But I've also done work on using genetic algorithms to tune generators to other things, and it could be something we pursue. But in this case, since we have the input-output example, we can condition it directly rather than having to do like a genetic optimization thing. Yeah, so that's the great question, is how much have we tested it? So we've tested it, like we've tried it on examples that exist on Stack Overflow. I think there's still huge opportunities to actually talk to users about, what is the way they really want to provide this input-output information, I think, but we haven't gotten there yet. Is that also a question, or? So is the question, what if there's multiple programs that can go from the input to the output? Yeah. In that case, again, we're mostly working on finding the first one right now, because that's actually still a super challenging problem given the breadth of this API. But after we get to that, then I think it would be we could also probably use some data from the real world to condition, what programs do people like the best, to deduplicate between different ones that you might return. Yeah. Yeah. Yeah, so the question is, like, do we have tools to help people create the output in the first place? I know at some point Rohan, when he was building the web interface, had some like fancier type of tools to help people write the output. Currently, the web interface doesn't have that, but I mean, we have been talking to other people in the RISE lab about actual usable user interfaces. I agree that it's, having the exact output there really helps us in the research domain, and I think it's a really interesting problem of what we can do when people are willing to specify some of the output or kind of part of what they want, but not the full thing. Yeah. Anything else? All right, then I'll let Rohan walk you through the AutoPandas process. Thanks.
All right. Can you hear me? Perfect. Cool. So as with Modin, the AutoPandas tutorial is hosted at rise.camp. You should see a link, AutoPandas Atlas, that should lead you to this Jupyter Notebook page, and I want you to open the AutoPandas pivot tutorial. There's also a solved one, but I intend for that to be used at the end. Not at this point. So if everyone who wants to do the tutorial can open the AutoPandas Pivot Tutorial Notebook, that'd be great. All right. I'll assume people are on their notebook at this point. I'm sorry? Oh, sure. Is this better? All right. So as I said, the tutorial is hosted at rise.camp. You should see the rise.camp where Modin was before. It's the same link. Yes. Do you see this screen? Cool. So I want you to open the AutoPandas Atlas link. That should take you to this notebook listing. Is it working? Cool. So I want you to open the AutoPandas Pivot Tutorial Notebook. This is where some of the exercises are and what I will use to walk through the tutorial. Awesome. So as Caroline said, the purpose of this tutorial will be to walk you through the process of building a synthesizer for APIs such as AutoPandas. In particular, in this tutorial, we'll build a small synthesizer for a subset of pandas and see how, in the process of building it, see how we can improve its performance, and at the end we get a very efficient synthesizer that you can actually use for your own purpose. In particular, AutoPandas is what Caroline described. Here you see this Atlas, Atlas keyword. So Atlas is the system or the framework in which we implement AutoPandas. Atlas tries to serve as a generalization, and on top of which you could build synthesizers for other APIs such as NumPy, again, as Caroline mentioned. And as I said, what are we going to learn? So Pandas is a huge library. I hope Caroline has convinced you about that. So what we're going to do for this tutorial is focus on a single function in Pandas, namely the pivot function, and try to build a synthesizer for that. So pivot takes a number of arguments, and sometimes it can get pretty confusing. So our goal is to build a synthesizer to help improve productivity when using this particular function. All right, so I'd like to start with the first section, which is what is pivoting. So people, if you don't know what pivot is, let me try to explain it quickly. So let's work through an example. It's the best way to describe it. So if you're working on some data just such as the stock market data, it might look something like this. You have a symbol, date, and a volume of trade that happened on that particular date. But if the data is given in this particular format, it's quite hard to visualize what is happening. So if you wanted to compare the stock prices on different dates or compare against different companies, it's kind of hard to just glean that information from this format of the table. So what pivot does is it acts like a summarization function that kind of changes the format in which it displays data, so it's easier to gather such information. So for, on this particular table, if you say you pivot on the date column, keeping index as the symbol column, and then rearranging the volume accordingly, you get this particular table where the new columns are the dates themselves, the symbols become the new index in the table, and the trade volume is organized accordingly. So in this particular form, it's actually much easier to derive insights about the volumes themselves and compare against different data points. So as I said, pivot acts as this summarization tool that really helps visualization in this case. So any questions so far? Perfect. So now let's define the synthesis task. It's just the same as what Caroline said. So you have this, you specify an input data frame, an output data frame, and you kind of call a procedure that gives you a program that takes the input to the output. So in this particular example, I have encoded the two data frames seen in the previous cell as the input and output. So just if you execute that, you should see the same input output example. So input is the raw data that we had. The output is the new summarized table that we want. And our goal is to write a method called synthesize pivot that takes the input and output data frame as arguments and hopefully returns a program that looks like this particular one. So it finds the right arguments to pivot that produces the desired output. All right, so this is our goal. This is our goal for our synthesis engine. With me so far? Cool. So it's always good to start with a simple solution. We all know how to do synthesis. It's just search, right? So why not just write a brute force search? So what we're going to do is in this particular section is we're going to write a simple synthesizer that just searches all the possible programs in or all the possible argument combinations to pivot and check which one of them is correct and just return that. Okay, so that's why it's a brute force synthesizer. And in order to do that, we first need to define what is the set of possible programs. So if you look at the documentation of pivot as provided by Pandas, you see this long listing, which basically essentially says what the values of index columns and values should be, which are the three arguments that need to be passed to pivot. I don't want you to get through that. I'll summarize it for you. The three main points are that the index argument should be one of the columns or the value none. The columns argument should be only one of the columns, but not none. It's not optional over here. And the values argument should also be one of the columns or none, but it can also be a list of the columns of the data frame you're actually pivoting on. All right? So the set of possible arguments to pivot, which is the set of possible programs in our case, is therefore the cross product of all the possibilities for all the arguments, right? So this is the set of possible programs. Now how do we express this space succinctly? And now comes in the concept of generator, which is similar to the one Caroline described. So let's dive a bit deeper into that. With me so far, any questions to this point? Great. So let me try to describe what a generator is. And then for that, we'll try to write a procedure that produces all the two tuples of column names. So it takes an input and returns all tuples which contain two column names. This is just a toy exercise. It's not related to the synthesizer, but I'm going to use this to introduce the concept of a generator. So, so from Atlas import generator basically imports this generator decorator. And we're defining this function called gen column tuples that takes the data frame as an argument And then it selects the two columns that need to be part of the output tuple, and it selects each of those columns using this special operator called select, which takes in df.columns. With df.columns is the pandas API that returns the list of columns in the data frame. Similarly, it selects the second column using the same call, and then returns both of them as a tuple. So this is what that function does. And the add generator decorator basically converts into a generator. Now, if you want to see how it works, on the input data frame that we had before, if you say, if you invoke a for loop, such as for result in gen column tuples, which is this particular procedure, and dot generate on this particular input data frame, let's see what the output is. So basically, it prints all the possible two tuples that exist. So it kind of enumerates all the possible values that could be returned by the individual select calls, and prints all of the tuples as returned by the function in that case. So what's really happening here is this gen columns.generate basically returns an iterator that keeps executing the gen column tuples procedure over and over again while making sure that these two select calls return a new combination at every point. So the end result is that you get all the possible two tuples that are there. All right? Any issues so far? Just try executing it so we're at the same point. Cool. And I also want to point out that this iterator has kind of a depth-first behavior. So if you look at the output, you see that this, the second value in the tuple changes first as compared to the first select call. So the depth first is that the second select call explores all possibilities before the first select does. All right? So this is what a generator was. We wrote a procedure that generates all possible two tuples of columns of the input data frame. So this might provide you some idea on how to write a generator that produces all the pivot arguments, as I was saying before. So let's move on to the C part. And this would require to kind of play around with the code. I have an exercise over there. So the goal here is to write a similar generator that takes an input data frame and outputs all possible argument combinations that can be passed to pivot. So you can go on to this cell. So as I said, as you may have noticed, the pivot function takes 3 arguments: columns, index, and values. So for the columns argument, as I said, it should be one of the input columns. So I have select list of input df.columns. So this sets the first argument. I also, so now to select the value for the index argument, I also use another select, but now it can also be none in addition to the list input.df.columns, right? And now, as I said, the values can also be just a column or none, but it can also be a list of values. So there's like 2 possibilities here, whether you have like one single column as the value for the values argument, or it's a list of columns. So in order to decide between that, we kind of have a branch which says select, and your code here is what you're supposed to fill in. So let me try and work this out for you, so this makes some sense. So as I said, there are 2 possible options, and we need to be able to explore both the branches. So this is simply going to be all the possible values that can be returned by a Boolean expression. So it's going to be select true or false. Now, if select is true, I want the values argument to be one of the columns or none. So why don't you try and fill in this particular expression here? As a hint, you can take, you can look at the expression I have for the arg index, or the expression for selecting the index argument. If you have any questions, just shout out. So the purpose of the select is to select one of the columns on none, and it's actually pretty much the same as the expression for selecting the index argument. If you do have any questions, you can raise your hand and our TAs will come over to help you. So as I said, the purpose of this select is to select one of the columns or none, and this is exactly the same as the index argument, so the argument needs to stay the same. So I'm just gonna go ahead and fill that in. So again, this means that it can be one, a none, or one of the input columns. Right? Now, in the second branch, which is the false branch, you want to select a list of columns instead of just one particular column, and for that we use this special operator called ordered subset. So ordered subset, instead of just returning one element from the list of values that is passed, which is here is just the list of columns, it instead returns a subset, and the ordered basically means like a permutation, all possible permutations of such subsets. So once we've done that, we can return the set of arguments as a dictionary, which basically just sets the values of each of the arguments. So go ahead and execute this. If you're getting any errors, just let one of the TAs know by raising your hand or shouting your question out. All right. Any questions so far? I'll move on to the next step. I'm sorry, I can't hear you. Yes. So I believe the question is ordered subset only going to return a list of one element? Yeah, it does include all of them. So ordered subset. So this ordered subset is going to return all possible lists of however many columns. It can return a list of one column or a list of two columns and so on. And the ordered part is because pivot does change the output if you change the order of the list past two values. Does that make sense? Oh, I see. Okay. So the question is, what is the difference between if this returning a list of just one column and this particular branch, which just returns one of the columns? So actually, the pivot changes the output based on if the values argument is a list or just a string representing a column. We'll see an example later on, but this is basically trying to capture all the possible arguments to pivot that do actually yield different outputs. So this is like, this kind of alludes to the phenomenon Caroline mentioned, that these arguments have like so many different behaviors based on how you select the argument, so it's not easy to keep all of this in mind. So when we write a generator, we want to capture all of these constraints. So now, since we have this generator, we are actually ready to write our brute force synthesizer. So as I said, we're going to be trying to write a procedure called synthesize pivot that takes input and output as arguments. And in this particular case, we'll just simply enumerate all the arguments we get, which is represented by this line for args in an expression that I'll ask you to fill shortly. And for every arg, we'll actually execute it. So we're calling here input pivot and passing the arguments to pivot. We're going to be checking if it's equal to the output at all times. And if it is equal, we're just going to print the set of arguments as the solution, right? And we do have a try-catch block around this, because if pivot throws an error, we don't want the synthesizer to just give up and just move on to the next argument that's going to come up. So for this particular expression, your code here, we basically just need to invoke the mechanism to get an iterator, as we did in the previous cell. So what we need to do is use the generator we defined in the previous cell, which is gen pivot args. And we want to get an iterator of all the possible argument combinations, so we call generate on it. This is afforded to us by the generator decorator that we had before. And the argument is just going to be the input data frame. All right? So now this defines the synthesize pivot method for us. And you can actually use this and try it out on the input-output example we had in the previous section. So this was the input data frame and the output data frame. And if we call synthesize pivot on that, we get the solution pretty quickly. It says the argument index should be symbol, the column should be date, and the values should be volume. All right, so our synthesizer is working. It's returning a solution at this point. And in the next section, we'll analyze the performance of this in a bit more detail and see where the problems are. But at this point, I'd like to make sure everyone is on the same page. If there are any questions, I'd be happy to answer. All right. So in the next section, as I said, we aim to point out the flaws in this brute force synthesizer in a bit more detail and see what can be done to improve performance there. So in particular, in the synthesize pivot, I'm going to add some more logging and some logging of statistics. In particular, I'm going to measure the time taken to reach, to find the solution. I'm going to count the number of programs that the synthesize pivot explores before finding the right solution. And in the end, we'll also kind of log how many programs crashed while searching for the solution, right? So let's go ahead and execute this. And execute it on the same running example that we have. So it finds the same solution as before, because it's the same input-output example. But we see that it took about 0.17 seconds to get to the solution. It explored 99 argument combinations before getting to the right one. And a number of programs crashed, 57. So this implies a number of things. First, 0.17 seconds seems small and usable at this point, but as we'll see, it's really not the case. Just for pivot, it's actually pretty slow. And imagine this in the bigger context where you have the full Pandas API, where you're building a synthesizer for all functions. Then this is only going to grow exponentially and make your synthesizer really not usable. And the point, another main interesting point here is that we crashed 57 programs. So there were 57 argument combinations that were returned by a generator that actually caused an exception. So if you see, if the synthesizer is spending time evaluating these arguments, it's just losing time. It should not really focus on these argument combinations in order to speed up the search, right? So in the next section, we're going to explore how we can add some more information to the generator that can alleviate this problem. So in particular, there's some domain-specific knowledge or some knowledge about pivot that is known to the API expert, which is, in this case, that for pivot, the columns and index argument cannot actually be equal, otherwise it will throw an error. So this is this is a detail that is actually known by the developers, because they are the ones who designed pivot that way. Another constraint is that the values argument should not contain any column that's equal to the one you set for columns and index. So this is like domain-specific knowledge about pivot that you already know. And We can incorporate these constraints directly in the generator. In particular, while selecting the value for index, instead of just doing none and all the possible columns, we make sure that it's not equal to the column you selected for the columns argument for pivot. You do the same for the select an ordered subset for the values argument. So the point of this generator is that you can incorporate these constraints seamlessly because they're just regular Python code. You can write them directly. You can encode them as regular code, which is far simpler than moving to any constraint language or designing a special language for doing the same. So if you use this new improved generator that prunes away bad candidates at the very beginning, and if you invoke the synthesize pivot method as before, you find that it's much faster now. None of the argument combinations crashed. It exploded a lot fewer argument combinations before getting to the right one. So we have an improved synthesizer at this point. All right. And this is because we're not wasting time exploring bad candidates. Cool. Any questions so far? Perfect. Now in the next cell, I'm going to point out the even bigger flaw, which you may have guessed because I've been mentioning brute force synthesis till this point, is that if the space of possible programs becomes very large, just exploring it in a brute force manner isn't going to help. In particular, even for pivot, if we were to pass big data frames, by big I mean there are a lot of columns, for example, then our synthesizer will suffer. So even in this case, we were working with stock market data, right? It's not unnatural to imagine the table we are working with is actually big. It's like a common database used for many analyses. So you'll have more columns such as the open and close values of the stock price or highs and lows. And your table would actually look more like this. And even if you wanted the same output as before, just focusing on the date symbol and volume columns, if you run the synthesizer on these two new, this new input-output example, you'll see it takes quite a bit of time. This is because if you analyze the generator closely, it's explore, so especially the values argument, the ordered subset function, is going to explore all possible lists of columns, and when you have a high number of them, this value just grows really big very quickly. And as you can see here, it took about 12 seconds to find the solution, and it had to explore around 6,000 programs before getting to the right one. Now, if you were to use the synthesizer in practice, this may be fine for your own personal use, but if you wanted to deploy this as a service, as we did in AutoPandas.io, this is clearly not feasible. This is clearly not real time. And also, if you had more functions, this time is only going to get worse. And in total, it had to explore 27,000 argument combinations before exhausting the space. So at this point, we built a brute force synthesizer, but it's not performing as well as we want. So let's try improving it. In particular, we want to train the generator so that it reorders the, so it explores the different argument combinations in a different order as conditioned by the input-output example that is provided. So in particular, in the brute force thing, we've been using a depth-first strategy. So we've systematically explored all the values of the operators. But the question now is, can we use a different or smarter enumeration order that is conditioned on the input-output example, so the generator yields the most promising candidates first rather than towards the end. And that can potentially help the speed of synthesis. And this enumeration order is entirely governed by the operators themselves, so the select operators, the ordered subset operators. So if they start returning the correct values first, it means the generator as a whole will return the most promising candidates first, and we'll get to the point we want to get to. Sorry. So in order to do that, first we need to give access to the input-output example to the generator. So if you've noticed the generator itself, the gen pivot args was only taking the input data frame as an argument. So now let's provide it, give it access to the output as well so it can make use of that information. So we modify the gen pivot args procedure. Instead of just taking the input, it also takes the output as an argument. And in this particular exercise, we'll try to train the first select, so which is selecting the value of the columns. So we'll kind of try to train this select to pick the right value first. So for doing that, I'm passing in this context, which is the input-output tuple. So context, I'll get to what context does, but basically this is providing some context to the operator as to what it needs to condition the order in which it returns the columns. And this UID is basically something that needs to be provided in order to specify a model, which we'll get to. But the high-level point here is that now we're providing access to the input-output example to the generator. Now, let's execute this. We also need to modify the synthesize pivot just a bit because we're now providing both the input and output instead of just the input. And just a minor change, we're also going to break at the first solution because we don't want to explore more. So we're just looking for the first solution. All right. So at this point, we've provided information to the generator as to what the input-output example is. Now, we'll try to define a model, specifically a neural network model, that for this particular select, we'll look at the columns, and we'll also look at the context, which is the input-output example, and then return the columns one by one in a specific order, which it thinks is the most promising for getting to the right solution. And so getting into the details is out of scope for the tutorial, but I'm just going to give you a few salient points of what this model does. So our model is a graph neural network, which takes a graph encoding of the input-output example. And the reason behind using graphs is that given an input and say output example, it's not really the concrete values in the table that matter, but rather the relationships between the elements that really capture the transformation that's being performed. So for this input, if you wanted to do pivot on that based on the category, data, and expense columns, it's enough knowledge for the model to know that this particular cell value is now becoming a column in the output rather than their value lunch itself. So what our graph encoding does, it basically abstracts away this unnecessary information. It just retains, say, the types of what the values are, and then retains these relationships as edges in the graph. So you see that this particular node, which corresponds to this lunch cell here, has an edge to this particular column, which corresponds to this one in the output. So it's retaining that these two values are equal, but it's throwing away the information of what the actual string is. So this really helps it generalize. So it doesn't, so the data we give it can be actually random strings for all that matters, but it still learns to do the right thing on unseen data. That's all. So if you want to dive into more details, feel free to look at the code as well as an upcoming paper that we have on this project. But let me move on to the next one. So in this next cell, I define the generator model that we're going to use. In particular, for that particular operator, which we were focusing on, the first select, which decides the value for the columns argument, we're specifying a model. We're specifying some hyperparameters for the graph model that we have, learning rate, node dimension, batch size, etc. And we're just returning, instantiating a model based on that. So let's go ahead and execute this. There are deprecation errors, but that's the case with TensorFlow. Anyway, so we've defined the model. Now let's get some data. In particular, the data, in our case, would be of the following form. You have an input-output example, and you want to kind of track. So you're training a select operator, right? So you kind of want to train the select operator to make the right choice at each point. So our data for this task basically has the input-output example, but also contains the choice that needs to be made by an operator. You don't need to go into details. You can always refer to the code, but the key point of this is that it keeps track of all the choices that need to be made by the operators so they can function as training data. Another important point is that this data is generated randomly. So we just take a random input data frame. We kind of execute the generator to get many programs, and we randomly select one of them. So that's why if you look at the input-output example over here, you see a bunch of nans and data frames that really don't look like something a human would write. But that suffices for our purpose, and as you will see later on. But yeah, this data is basically these traces of what choices operators need to make. So now once we have the data, we can start training. So we define the model. We just instantiate a model using the class we had defined before. We split the data into two parts, the first 500 being training, the rest validation, and we kind of start training. So the API manages all the boilerplate for you. It's going to take about 30 seconds or so to fully train the model for this particular operator. And it achieves quite high accuracy. And the major reason for this is our use of graphs as encoding and a graph neural network as the model itself, because it helps it generalize pretty well, because we're just throwing away arbitrary information such as the concrete strings or numbers within the tables. We haven't focused on that yet, but I'm sorry. So the question was, have we tried to use this same technique for, say, MySQL kind of schema transformations, because they're pretty much the same as the ones in Pandas. So we haven't really built a synthesizer for that as of yet, but we do believe our generator approach can encode such an engine pretty easily. But we haven't instantiated that. It's in the works. It should, because the graph encoding is really good for schema transformations, because these relationships are very easily available, and the model learns them pretty well. And in this case, as you can see, we've achieved 99% accuracy pretty quickly. And if you incorporate it into the synthesis engine, you see that by doing generate, we call a with model. So it starts using the model for enumerating the arguments. So if you execute that and run synthesize now, you see that it finds the solution much faster, because it picked the right value for the columns argument in the first try. So here, this list that you see here is basically the predictions made by that model that we just trained, and it picks date with 96% confidence. So it's been trained to perform that very specific task, and it's learned that pretty well. So far so good. We've trained one operator, and it's significantly sped up the search. We're down to 4 seconds now instead of 13 or 11. I don't remember, but it was high. But can we do better? I mean, why just train one operator? Can't we define a model for all the operators, for all the selects that we're selecting values for the other arguments as well? And that's exactly what we're going to do now. So in this particular section, we define a model for all operators. So instead of just having a context for the first operator, we're going to do the same for all the selects and ordered subsets that we saw. So you see context being passed here. You see context being passed here, as well as here. So we've provided that same context of input example to all the operators, and we define the generator accordingly. We define a model for all the operators now, instead of just one. You can always go back to this tutorial to dive deeper into the details, but let me jump. So you can train this model using the same set of commands I had before. The data is available online as well. But it takes about 10 minutes to train all the operators. So I'm just going to skip ahead and download a pre-trained model for the same task. It's been trained with the same set of commands. So I'm just going to restore it from that particular link. So it takes a bit to kind of load the model weights, warm them up, and make them ready for the generator to use. Perfect. So we've restored a model that we already trained before by pulling it from a URL. Now here's the meat of our approach. Now we can use the synthesizer which has models for all the operators and see how well it performs. So given the same input up example, now it finds a solution within the first try. And it's the same big data frame example we had before. Similarly, if you take the running example we had, it again gets it right on the first try. And let's say I try some more data frames. So if your input up example looks something like this, it has generalized pretty well. It finds the solution again in the first try. There are some other examples as well if you want to try them out. I'm sorry, yeah. So the question is, can we do joins? We do. Actually, there's an example on autopandas.io where you provide two tables and you have one particular output and it figures out how to do a join in the same case using pandas. So I'm almost out of time, but at the end of this tutorial, what we've done is we've built a synthesis engine for just one function in pandas, which is the pivot. But we train models to make that really efficient. Now it's like actually the optimal synthesizer. It gets things right on the first try. It is as fast as you can be. And in AutoPandas, actually, we define a generator for all the functions. And we can also synthesize sequences of functions, as you saw in the demo. But the approach still remains the same. It's the same. It's just a much larger generator, but we kind of define models for each of the operators, so they learn to do very specific tasks really well. And at the end, you get a synthesizer that's really, really fast. I'd be happy to take questions. I'm almost out of time. And, yeah. Yeah. Yes. Yeah. So the question is, how well does this do if you're dealing with sequences because you don't have access to the intermediate outputs from, say, the first function? So actually, the burden of that is on the sequence operator, which initially figures out what is the sequence of functions you want. So it looks at the input up example and figures out all the functions that you need to use. And because the way we structured the generator, the intermediate output is available for predicting the arguments of the second function. For details, you can refer to the generator that we have, actually, but it does give it access to this intermediate output.